When you see an alkyl halide or an alcohol treated with specific reagents and conditions, you need to know what products to write. You need to consider whether it's an elimination reaction or a substitution reaction. And you also need to think about whether it's an E1, E2, Sn1 or SN2 reaction. There are enough details about these that you could go cross-eyed, almost crazy, trying to sort everything out and figure out what products to draw. I've got good news. It's much simpler than that. There are just a few considerations about each of these mechanisms that you need to keep in mind. Let me show you those, and then we'll apply them to some reactions. So we're looking at factors that favor individual reaction mechanisms. And let's do substitution first. The SN2 reaction is favored by a strong nucleophile that's a weak base. It's favored by primary halides or tosylates, and polar aprotic solvents especially favor the SN2. The Sn1 mechanism for reactions is favored when there's a weak nucleophile and weak base. The substrate is tertiary, whether it's an alkyl halide or an alcohol, and you're using a polar protic solvent. As well, there are just a few characteristics that strongly favor elimination. First and foremost, heating, using higher temperatures, strongly favors elimination reactions. Regarding reaction mechanisms, the E2 reaction is favored by a strong base, and the E1 reaction is favored by a weak base, weak nucleophile, tertiary halides or alcohols, and use of polar protic solvents. You see that E1 and Sn1 are both favored by the same kinds of characteristics, which gives you a strong hint. There's a really good chance you're going to see mixtures of substitution and elimination for the first order reactions. Okay, let's look at examples of several reactions. First of all, it simplifies things enormously if you focus first on the structure of the starting compound. When the substrate is primary, Sn1 and E1 are simply not possible, so we can rule those out. So let's look at some examples of primary substrates. When this primary bromide is treated with the sodium salt of methane thiol, it's being treated with a very good nucleophile. So we first notice that it's a primary structure, and the second thing we put down is that it's a very good nucleophile. We can promptly conclude from these two things that this is an SN2 reaction, and so the product is simple, direct replacement of the bromide. Here's the new nucleophile. When we look at this same bromide treated with potassium tertiary butoxide, again, we see that it's a primary substrate, and it's being treated with a strong, bulky base. The bulky base means that it's not a good nucleophile, so we'll see elimination. This has to be E2, so the product's an alkene. Again, the same primary bromide is treated with a strong base, but this time it's not a bulky base. It's both a strong base and a good nucleophile. So the substrate is primary, we have a strong base, we have a good nucleophile. The strong base tells us there should be an E2 reaction. The good nucleophile tells us there should be an SN2 reaction. So we should expect a mixture of products, the alkene and the substitution product, an alcohol. Now look at this alcohol. It's a primary starting compound treated with concentrated sulfuric acid and heat. The primary substrate, weak base, weak nucleophile, strong acid catalyst that makes a very good leaving group. Together with heat, this tells us we have an elimination reaction. Because it's primary, we know that it must be an E2 mechanism. We'll expect this alkene. So primary substrates are pretty straightforward. They're only SN2 or E2 reactions. Next, let's look at tertiary substrates. They're also really straightforward. For tertiary structures, the SN2 reaction is not possible. Treatment of this tertiary alkyl bromide with potassium tertiary butoxide uses a strong, bulky base. So we notice right away that it's a tertiary structure, that it's a strong, bulky base, and we know that it's an E2 reaction. Using the bulky base, regioselectivity preferentially removes the less sterically hindered proton. We make the less substituted alkene. This is often known as a Huffman product. When the same tertiary bromide is treated with a strong base that isn't bulky, we see the other regiochemistry. This tertiary substrate, treated with a strong base, undergoes an E2 reaction, but now the regioselectivity follows Zayseff's rule. You make the more stable, more substituted alkene. The double bond has more alkyl groups attached. When the same tertiary bromide is treated with methanol, we have a different outcome. It's a tertiary substrate. We have a weak base. We have a relatively weak nucleophile, so it must be an Sn1 or E1 reaction. Because we don't have a good base, we'll expect a substitution rather than elimination. If this tertiary substrate is an alcohol rather than a bromide, and we're treating with the strong acid HBr, we have a tertiary alcohol, we have an acid catalyst, and we have a strong nucleophile. When HBr protonates the alcohol, it makes bromide. Under these conditions, we'll expect an Sn1 reaction, as we saw up above. But when this alcohol is treated with a different acid, one that doesn't make a good nucleophile, we see a different outcome. This tertiary alcohol is treated with a strong acid catalyst, but we have a weak nucleophile. Under those conditions, we'll see E1 elimination. Now let's look at some secondary substrates. They're a bit more complicated because more possibilities exist. Both elimination and substitution, and both mechanisms for each are possible. There's a secondary structure that shows stereochemistry. It's a single stereoisomer. We notice that the reagent is a strong nucleophile and a weak base. It must be an SN2 reaction. SN2 takes place with inversion of configuration, so we'll have to be careful to show that. And if the person running this reaction wants to be sure that it's an SN2 reaction, you know that you can use a polar aprotic solvent like DMSO. When the same substrate is simply treated with methanol, now we're looking at a weak nucleophile, a weak base, secondary substrate, and notice that because methanol is also the solvent, we have a protic polar solvent. This definitely promotes the Sn1 reaction, but we'll see some Sn2 reaction too. We should expect a mixture of reaction mechanisms. Sn1, probably the major pathway, and Sn2. Sn1 creates equal amounts of the two enantiomers, inversion, as I'm showing here, and retention, while Sn2 creates only inversion. So there'll be more of the inversion product and less of the retention product. When the same bromide is treated with still other conditions, strong base and heat, the strong base tells us it will be elimination, a good nucleophile, so there may be some substitution, and heat, which tends to favor elimination. We'll expect E2 and SN2. It's a small base, so we'll expect the Zaysseff alkene, the one that has more alkyl groups attached. And it's an Sn2 reaction, which proceeds with inversion of stereochemistry. So we'll expect this enantiomer of the alcohol. And finally, one more example. This same secondary bromide treated with a strong bulky base in heat. That bulky base is a poor nucleophile, and the heat favors elimination. So we'll expect the E2 product. Because it's a very bulky base, we'll expect that it produces the Hoffman product, the one with fewer alkyl groups attached to the double bond. So with the bulky base, we see the Hoffman product, and with the much smaller base, we see the alkene is formed according to Zayseff's rule. So returning to the factors that favor individual reaction mechanisms, applying this relatively small number of key characteristics of substitution and elimination, you can draw reaction products with confidence